so I'll just go straight to the slides. Hopefully the sharing screen will work. And this one. And view. Oh, hi. So I would like to talk about one of my current projects, which I've been thinking about for some years, and it's a kind of an amalgamation of a whole bunch of things I've been thinking about for maybe 30 years, and I think it's quite promising. Before I do, I'd like to talk about John Crossley, since it's an appropriate time to talk about that. So I should say, how did I even get to Monash, and why did I do logic? So I was when dinosaurs ruled the earth in 1979 to 81, I was John's PhD student long ago in Monash, and I was sent there by someone called Neil Williams, who was a co-author and a set theorist at Queensland Uni. And he was, sorry, a typical typo, because I did this very recently. He was one of the authors with John on that book that I admire very greatly, and I give it to many people, which is a thing called What is Mathematical Logic? Oh, there it is. What is Mathematical Logic, which is an excellent book. And whenever someone a student wants to know about this, I say, read this, and you'll learn some stuff. And even today, I think it's one of the most beautiful introductions to logic that I'm aware of, at least certainly mathematical logic. And down there in Monash, so I work with Neil Williams he gave me two choices for an honours project. One was the Eklof-Fisher work on the elementary properties of abelian groups, and the other one was the decidability thereof. And the other one was something about small, large cardinals. And I looked at small, large cardinals, and I thought I'd never want to be a set theorist. And I still have this feeling that I never want to be a set theorist. But on the other hand, I kind of like doing effective mathematics, and I had a reasonable feeling for doing things without knowing the theorems, just doing them from basics. So I said, where can I do this? And he said, the only place you can do that in Australia is at Monash, and you should go down and work with John Crossley. I thought, okay. And I must say, my heart sang when I left Queensland. I thought, I'm never coming back here. And I loved Melbourne, and I enjoyed my time at Monash. I have very fine memories of those days. There was John's got this humongous office with, back in those days, there was no internet, there was nothing like that. It was extremely important that you had access to papers and what was going on in the world of mathematics. And every so often you'd bundle up things and send them to people. And in fact, one of my first research grants I ever got was in Singapore, where I got a research grant to send out preprints. And you know, it was so it's hard to think of those days. I remember reading John's thesis, and he thanked someone for keeping the stencils, which I think anyone under the age of maybe 40 couldn't even imagine, that you had to have someone keeping the stencils so that it could be copied. So I have lots of fine memories of those days. Anne-Marie Vanderborg was John's secretary, who kind of protected him like a mother hen and did lots of stuff like that. We used to have a weekly seminar, or at least bi-weekly seminar, and that was always kind of fun. Chris Ash and I used to smoke then, would sit in the back smoking cigarettes and going, that was in the days when to be a philosopher, you had to have a pipe and kind of pull it out every so often and say things like that. So at the time I was working in computable model theory, particularly matroids, independent systems, Steiner's closure systems, and Boolean algebras. And one specific thing I'd just like to mention, I'm not going to talk about my thesis that much, but was what are called Martin-Perel theories. It's not really important what they are. They're axiomatizable theories with few extensions, but the project was to show that there's a certain Turing degree you can associate with it, and they exist in every computably enumerable degree. And I had a visitor, John had a visitor, one of his many visitors, and someone called Jeff Remmel, and he said, just do this, it can't be that hard. And I worked on this, and I thought, God, I'm stupid, how can I not do this? And then I suddenly realized at a certain point, which was a seminal point of my thesis, just it's not true. And to answer the question, I realized that there was this strange phenomenon going on, and I kind of worried about that for years. And for 40 years, I've been thinking about off and on this project, and eventually it turned into a project with Noam Greenberg and others. And there's now a 200-page book in the Annals of Mathematics Studies whose direct roots go back to my thesis. So when I think back on my PhD days, the intellectual legacy definitely goes back to then. So I'm very thankful for that. It was a nice little group. John Stewart went to America. Chris Asher, unfortunately, committed suicide, but back in the days, it was very nice. Anyway, John was always happy to move areas. And so when I finally got a job where it was a tenured job, I actually started teaching computational complexity theory, because I thought, well, maybe I'd like to learn something about this. What I'd like to do today, the work I'm going to talk about, is about a finitization of work on computability theory, along with ideas from computational complexity theory, particularly parameterized complexity. And the reason I find this interesting is because my intuition is that when we're doing, when a computability theorist or recursion theorist, if you're very old, does what they do, they're really dealing with finite strings or finite structures. And you're really talking about uniform operators on these things. So even though it doesn't appear, I mean, it's very striking when you think about computational complexity, how discontinuous it is. You vary the input just slightly and you get a completely different answer. So this is what I'm going to talk about. But before that, I'd like to say all the best to John. Congratulations on achieving. I can't see myself living to 85, but wow. Okay, so let's do some math now. So what's an online algorithm? So your job is to put an unknown number of objects, which are being given to you, of a certain maximum capacity, and they're given to you one at a time. And you must put an object AI into some bin, and you just get to, and you put it in, you can't take it back out. So you're packing the car and you're putting things in the car, and the children are bringing them down to you, and you don't know what order they're coming. And so how are you going to go? Or here's another example. I'll give you an unknown graph one step at a time. And I'll give it to you by the induced subgraph. So I give you a vertex and I say, here's what it's connected to on the current graph. I'll give you another one. Here's what it comes to the next one. And what you have to do is you have to color it. You say, what color should I choose? I'm going to minimize the number of colors. Or you're in a vast graph. And you're a humongous database and you need to build some object incrementally. But you can't see more than a small distance around that point. You can't do more than local search. You're navigating a robot somewhere. Or you're a triage nurse at some hospital and patients are arriving and you have to have some priority ordering, which are words I like very much. And you have to say, where do these people go? So, or you're answering questions about an infinite group on your laptop, which is actually what people do. And you have no idea about the complexity except hope. You don't know how long it's going to take. So all of these situations, you're in an online situation. Now, if you think about, if you've done any courses in graph theory or anything like that at university or taught them, most computational complexity assumes that I give you the object as one chunk, and then you have complete access to it, you know about it. Whereas in many things, you have no idea how big the thing you're dealing with is or what's going to happen in the future. There are hundreds of algorithms that need this. A scheduler needs to give memory allocations. So, and there are books and books with taxonomies of such algorithms. It's really an extremely important area. And as data gets bigger, there's no doubt in my mind that algorithms concerned with incremental changes in data and the relationships with the updating solutions become ever more important. You can't think. I mean, my university, when it timetables, starts every year the same way, wiping everything. This doesn't strike me as the most sensible situation. Mostly we start with some kind of solution, so how can we improve it? Now, this is an area with huge amounts of algorithms, but very, very, very little theory. And what I'd really like to do is try and give a theoretical basis for this. What's a good setting? What kind of questions can be answered? Can I give some logical description of the objects that I'm studying and perhaps get an automated way of generating algorithms such as Courcell's theorem in finite graph theory? What are the best parameterizations here? What's the way of breaking the data down which will make things accessible? And I'm going to talk about two wee bases. I don't know the extent to which I'll cover these slides because there's a lot of them, and instead of which I'll just select from them. But one such basis has been talked about by one of my students and one of my postdocs, Sasha Milnikov and Inkang Meng. And I'll just mention that one first. And there's another one that Melnikov and I are currently generating. So There seem to be two basic criteria for being online. One is that they're not independent. The first is based on what I call punctuality. You have this thing which has arrived, right? You have this thing, something's come into your database, a graph, a vertex has come and said, oh, I'm connected to all these vertices. And before it leaves the page and before you get the next one, you have to make a decision. So you have to make the decision punctually. Right, so this is a growing, a rich theory and intersects with something called temporal graphs, which I'm not going to talk about, but it can be put in this setting. And the second's based on what I call the uniformity of the operators. And you're playing against a hostile universe. The universe is a nasty place, and the universe is trying to trick you. So it has no theory yet at all, as best I can figure out. So what's punctuality? Well, there's lots of different choices you could make, but I like the way it enriches computable structure theory. So, and a good way to understand it is consider the proof that we tell any first year student or any first year graduate student that a computable dense linear ordering without endpoints are computably categorical, meaning that give me any two copies, I can use the back and forth argument to generate an isomorphism. But suppose my task is to build a quick isomorphism, and suppose A and B are quick copies. I'm giving you the vertices. So I have two vertices, one here, and something comes between them. If the other side's not very punctual, there's no guarantee that there will be a vertex arriving in time to send it to on the other side. So there's no obvious way to quickly build an isomorphism. I really have to wait. I have to wait for that thing to come up. But on the other hand, if A and B were giant cliques, there'd be no problem because all you do is map anything to anything because they're so homogeneous, there'd be no problem. There is a logical comment that if you had fast Skolem functions, you'd be okay because you have to realize sigma 1 formulae. So this structure was modeled by these Kalamulin, who's from Kazan, Melnikov, and they had this notion of a function being structure being punctual if its domains are natural numbers and its relations and functions are primitive recursive. And lots of people have kind of had this idea. Why primitive recursive? Why not some other total class of total functions? Well, because it's the nicest class that we know, which has a nice Church's thesis. Namely, I'm computable without while loops. And it's not really dependent on how you represent the data, whereas things like polynomial time or automatic or things like that really matters. So from a logician's point of view, I think one of the classic theorems that we always learn, if I give you a decidable theory, it has a decidable model. It goes back, well, Terry Millar's paper even earlier. But more importantly, almost any normal decidable theory is not decidable. It's decidable in like double exponential time or triple exponential time. I mean, you've got to go out of your way to make a theory, a natural theory. I mean, any of that stuff done by Gretty Herman or any of those people that millions of years ago, the 1920s, any of those decision procedures from algebra, they're not they're not total computable functions which are not primitive recursive. They're very low-level algorithms. So almost any normal decision process arriving in classical algebra or analysis, it'll be primitive recursive. So it's relevant to, from a logician's point of view, to what we study. And it's tempting to suggest that if I have a primitive recursive decision procedure, that I have a punctual decidable model, but it's not true. And the reason being because primitive recursive means I just tell you whether something's true or false. If I give you a formula, that I'll say yes or no. But if it's an existential formula, if you need to build the model, if you think about the Henkin construction, then what you need is you need to know, give me a witness. So if you have primitive recursive Skolem functions, you can actually prove it. So a primitive recursive decision procedure has a punctual decidable model. And the next thing's a counterexample. If you don't have this primitive recursive decision procedure with computable, and the proof's due to Henkin, actually. It's a very pretty theorem, actually. Do I want to talk about this? It's a bit technical. You can prove lots of technical stuff about this that you can say, well, okay, suppose I do have these Scholar functions. Am I isomorphic to a good one? And you can ask lots of questions. These are the kind of questions that I think that we ask when we do computability theory, particularly when I have this student ask us who's a master's student and you're looking for a nice project. And there was for those of you that like these kinds of things, that was a very interesting infinite priority argument to prove that. So it's non-trivial what goes on here. And there's a very rich theorem. You can prove some general soft model theory that if I have a primitive recursive decision procedure, then you have punctually decidable prime models, and then you can omit types if you want to. And there's lots and lots of stuff, but it's really still an area completely waiting to be developed by some student who's keen and willing to pay the punishment. And more interesting possibly is the hard model theory, where you're studying natural structures, and the following things have punctual presentations if and only if they have computable ones. And there's a list of them. These are the familiar things we're used to: linear orderings, Boolean algebras, things which are reasonably homogeneous. You can't be too rigid you can't have examples which are highly rigid, because you can do a lot of coding in them. So locally finite graphs, abelian P groups, and so forth. On the other hand, there are things which have computable structures with no punctual representation, and torsion abelian groups, of course, you can code into the P groups, and graphs, and Archimedean order groups. So you may say, well, how hard is it to figure out if something's has one of these things? And the answer is extremely hard indeed. This is a theorem by Bajanov, Harrison Trainer, who was a postdoc, Callum Mullen, Melnikov, and this is not an easy theorem at all. It's an extremely complicated theorem. Namely, I have a punctual automatic or polynomial presentation. If I look at that index set, it's sigma 1 complete. Now, sigma 1 complete is really bad. Sigma 1 complete means it's as hard as computing whether or not a tree in bare space is well founded. So these are extremely hard problems. Now, I have worked in that, but I don't really like, I don't think it's the right model. And I think the right model is the following. So a criticism of the above is there's another aspect of the algorithms that we're doing. Consider the online problem of coloring a graph. I have a graph, I want to color it online. So the algorithm is this operator, it's acting on the GS plus 1, which is an extension of GS, where I've added one vertex. And for simplicity, I'm just going to say it has to do it immediately. I'm not going to wait for any number of steps. But the thing is, it just acts on this sequence of graphs. I have a G0, a G1, G2, and it has to act continuously as a continuous function, continuous computable function, or functional really. So it's the offline algorithm is a sequence of algorithms acting on the given graph. The online algorithm must act on these graphs one at a time in a continuous way. Now, this is very, very, very similar to the way we think of things in computability theory. We think of functionals in computability theory as things acting on strings and taking strings to strings. And the same deal is I have an algorithm here, which is taking strings to strings. The first strings happen to be, for example, graphs, and the second strings happen to be colored graphs, for example. And they need to be continuous. And the key observation is, even though there's only a primitive recursive number of graphs of size S, there's no reason to believe that the limit graph that the opponent builds is even remotely primitive recursive, because there are uncountably many possible paths through the tree of all graphs, right? So the algorithm's acting on objects represented as paths through a tree, and is simply an operator on such a tree. So what are we studying? We're studying operators on a tree. Now you could argue that any online thing can be somehow slowed down like this, but in practice, because this is about practical mathematics, normal structures are given in layers. I mean, a graph is giving you the next vertex and the next vertex. It's not like I'm giving you like one edge at a time slowly or something like that. So we want a theory that reflects practice. So based our ideas on this, we come up with the following definition. A class of relational structures is called inductive, or if all of its initial segments lie in the class and it has a filtration, namely, or a punctual presentation, where each S is finite and has universe 1 to S, or something more or less the same as that. And for all S prime bigger than S, if you look at AS prime, then AS is the induced substructure sitting inside of there. Now, if you want to do this as a recursive analyst, you can actually, or a computable analyst, you can actually talk about representations. And the way you represent these things is just think about them as being represented as passed through bare space. So that's bare space over there, the class of all finite strings. And the functional F is acting on the strings, taking strings to strings. Think about it as taking graphs to color graphs. So an online problem is simply a triple. It's an instance, the space of outputs, the space of possible solutions, and the algorithm S, right? And what I'm seeking is, so this is the space of solutions will be the collection of colored graphs. And what we want, as it says down here, we want an online solution, simply something's computable without delay. It is a solution, it is a coloring, and it's only using the information from S in its computation. So it has to act continuously, without delay, and it's acting only on sigma. Every online algorithm that you can pretty well think of has this property. And so it's a nice setting. It's what it's saying is, it's saying that when you do online algorithmics, you're basically doing computable analysis, which is kind of an interesting thought. So the key difference from the punctual view and the view here is this is a type 2 theory rather than a type 1 theory. And for example, suppose that the representation's Cantor space, there are uncountably many structures represented as paths. It's the algorithm acting on the paths which must be uniform. And the primitive recursiveness needs to be relative to that path. Okay, and the point is, if you think about things this way, then there's no difference between finite and infinite. So if A acts in an online fashion uniformly on all finite strings, then it acts uniformly online on all computable paths. And if the algorithm's total and it acts uniformly on all computable paths, then it acts uniformly on all paths. So then the proofs are really easy because things are dense, really, essentially. One's a compactness fact and the other one's computable paths are dense. So there is no difference between being infinite or finite. And I could write this out in more detail, but I'm not going to because it's not going to help. Okay. And then you can say, well, okay, so far so good. We had this previous punctual setting for the type 1 example. And you could say, well, okay, does anything lift? And it turns out in the previous setting, there are lots of things which are categorical, meaning that all copies are isomorphic by punctual isomorphisms. What about these things? And it turns out that if a relational structure is on a categorical, it's essentially totally automorphically trivial. It means it's either basically a humongous clique or a humongous anti-clique. Think of it as a graph. So nothing happens. So the theme in the theory tends to be smoother and surely involves definability and forcing than a corresponding punctual theory, as the punctual theory has no uniformity. Okay. So one of the underlying questions seems to be, what are the connections between uniform computable structure theory and type 2 computable analysis? And I think I don't know. So I'm just going to talk about some recent work that I did. I'm going to skip a few slides, but I'll just say, what are the issues, the kinds of things that we're interested in? And one of the things is what's called the performance ratio. This is things that computer scientists care about a lot. And let's think about it for a minimization problem. So I'm thinking about this as coloring again. So I'm looking here at, this is the thing at the bottom here is the chromatic number. And this is the number I get for coloring the graph using an online algorithm. And so what I'd really like if this takes like, I'm comparing, if this is taking, let's say it's a planar graph, this is taking 4 colors, how many colors do I need to color a planar graph? What's this ratio? And of those original problems I was mentioning, the bin packing problem, there is, if you just take first fit, put it in the first bin you see, that has a performance ratio 2. So the online version versus the offline version, you're not going to use anything worse than twice as many bins. That's quite a reasonable thing. You can't possibly expect to do it exactly because that's just, life's too bad. One example above is coloring, and sometimes you can be lucky. So if it's a planar graph, it's quite easy to show that for a planar graph, we know offline you can do 4, but you can't for n vertices do better than log n many colors. It's kind of like there's ways of making bad planar graphs where you're forced to use more and more colors. This goes back to some work of Bean from the 1960s. But sometimes you can do nice things. And there was a nice example of this. If I give you what's called an interval graph of with K, it can be online colored by 3K plus 1 many colors. This is a theorem due to Hal Kierstead and Trotter. And a graph's called an interval graph if it has this property. If I give you the graph, and for each pair of, and associate with each vertex an interval in between 0 and 1, and 2 intervals intersect if and only if this is an edge. Now you may say, that seem very strange graphs. Why would anyone care about them? These are exactly the graphs that come up with as memory threads. So these intervals represent memory threads in areas of shared memory. So if you're studying what happens inside a shared memory setting, you can actually often represent them by interval graphs. And the interval graphs are memory allocation problems is represented by using interval graphs. And one of the recent work I did, this was done about when I was writing up a paper for this conference proceedings. This can be generalized from interval graphs to partial interval graphs. Now, this may seem like not a big deal, but interval graphs can be can for example, be recognized very quickly in polynomial time. I think it's a linear time algorithm. Whereas recognizing a graph path with K, a partial interval graph, is NP complete. So it's quite surprising that this is true. So graphs of path with K can be online colored with 3K plus 1 many colors. And first fit colors such graphs. The best we've been able to do is K log K many colors. And for interval graphs, it's known you can do it in 8K many colors. I conjecture that you can do it with constant approximation ratio, but I don't know how to do it. Maybe if I work harder at it. How are we going for time? Okay, so I'll mention a little bit of that stuff at the end. I'm not going to go through these next slides in detail. I'll just say where we went. So what's computable analysis? Computable analysis is probably easiest to understand on Cantor space. And you can then study standard functions on, for example, the reals or whatever. And you think about what kinds of computable functions are online computable, meaning if I give you a bit sequence for one real and a bit sequence for the others, how hard is it to compute the sum? This is something people have studied off and on for years because these are basic operations occurring in computers. And just one example would be integration is you can do integration online Lipschitz computable with constant 2. So this stuff can be studied, and you can study standard analysis by looking at it through online eyes. And the idea would be I'm some machine trying to calculate some solution, and I'm giving you the reals, and I'm saying how hard is it to compute the relevant operation. I was going to talk about Weierach reducibility, but I think that's for a more specialized audience, so I won't do that. And these are ratio preserving Weierach reducibilities. So the point of these slides was, and I'll post the slides, of course, but the point of these slides is to say that you can now go and, as they say in New Zealand, uplift a lot of the stuff from computable analysis and say, aha, if you just put the right bound somewhere, all of a sudden the apparatus of computable analysis has analogs for online computation. That's a very nice thing, because it says, look, these people have been studying this stuff for years. If you miniaturize it the right way and parameterize it the right way, all of a sudden you have a set of tools that you can apply. And we've found lots of other applications, which I won't go into. There's a stuff called EX learning, which is EX means explains. It means I'm giving you a bit sequence for a function and you want to learn it in some learning algorithm. Distributed computing, that's processes talking to each other, and you can model those as pass-through trees. There's stuff called Buki automata, which is things like S2S and all kinds of interesting things in. And somehow these ideas all tie together. And I'll give you two examples, one from treaty compositions and one from proof theory. So we've already seen, so what I really like, what I really want to be able to do is be able to prove a theorem that says, so there's this famous theorem by Bruno Courcelle, which says the following. It says, look, if I give you a graph and it has, let's make it bounded path width, but it's actually bounded tree width, but let's make it bounded path width. And I want to know, does it have a Hamilton cycle? Does it have a typical problem, which is NP complete? And let's just be lucky enough we can write down to monadic second order logic. Just be very lucky. Then you can say yes or no in linear time. It's not good linear because the constants are bad, but nevertheless, you can say yes or no in linear time. And this is a very beautiful theorem, because it says, I want an algorithm. What do? I just write out the thing and I'll go, oh, monadic second order definable. Immediately, I know it's got a linear time algorithm. But this is an offline algorithm. I have to know the graph, and I have to compute the tree decomposition or the path decomposition. And then I build an automaton, and it processes a certain description of that object. So this is work going back to, in fact, you prove it with the Myhill in the Road theorem, or an analog of the Myhill in the Road theorem. Now, there is no hope of getting a theorem like this for the online situation. So this is the feeble attempt that we have so far. If I give you a formula on it, which is first order on graphs, and variables only, it's a minimization thing, and variables only occur positively or all negatively in 5x, then the online problem corresponding to it has an online algorithm, namely the greedy algorithm, which has a constant competitive ratio for graphs of bounded degree. Now, this is not the greatest theorem you'd ever prove, but it's a first theorem in logical descriptions. And we don't understand the kinds of logic we need to be able to do this. And so for those of you that know, I use Gaifman's locality theorem, which says first order formulae can't say very much. And then you use a lot of greed. So it says that perhaps first order logic is the wrong logic. So maybe what we need is another logic. And my guess is, did I put it here? My guess is the correct logic is probably continuous model theory. Continuous model theory was invented long ago by Chang and Kiesler in the 60s. And it really studies the logic of topological spaces, the logic of metric spaces. And what we're dealing with here is really a metric space. We're dealing with a metric space. So it would make sense that the correct logic probably should have something to do with analysis. So the logic of analysis is continuous model theory. And perhaps there's a miniaturization of this. I think probably it'll work for compact structures. I think you'd have a lot of trouble if it was only locally compact, but maybe not. You can also do delta 2 processes, and I won't, such as online bipartite matching and things like this, and the triageness, which I won't talk about. I'm just pointing out these are other things one could study. You could study delta 2 processes, and you can actually do finite reverse mathematics. You can say, you can actually count the number of mind changes you need and say, this one online reduces to this one if they have the same problem. So the idea would be to do finite. So, because my view now of reverse mathematics, it's really studying finite strings, because all things we do, they're always coded, and they're always talking about the uniform procedures that we study. If you can then calibrate how the extent to which these things change, then you know what you mean by, say, weak Kernig's lemma or arithmetic comprehension for finite structures. So I think there's a lot of really interesting work here, which I have, maybe I'll do in the next few years if I get time, or maybe I'll find enough co-authors to be able to do it. And so, so going back to our example of these good Skolem functions, imagine you're in a maze and you're navigating. Unless you're in a Harry Potter movie, you're going to know where you can go. It's not going to be all of a sudden some magic portal opens up and you can go through there. So if I'm navigating somewhere, I know where I am. So I actually have a lot more of a knowledge of the local situation. It's not likely new edges are suddenly going to appear. So then so the online structures lead to what we call online parameterizations. So something's locally strongly online. If I give you one of these representations, and I'll tell you what the neighbors are. And strongly online means I know all of the neighbors. So the first one's natural to a graph theorist, and the second one's natural to someone doing online algebra, because in online algebra, you're going to close it under functions, so you know where things are going. And you can think of think of it as, I'm sticking to graphs again. You can think of GS as the blue part of the graph that the algorithm has to run on, and H is the red part, which you have knowledge of, but you haven't yet processed. And the online algorithm is running on the blue part. And this goes back to old work again, highly recursive graphs. So again, the ideas from the past have echoes in work that we're doing now. And so Askers showed that if G is strongly online graph, it can be strongly online colored, and at worst twice the number of the chromatic number. And Askers showed that nevertheless, not everything from the old work can be lifted. So this is a direct lifting of a theorem of Bean, but Schmel's theorem is no longer true. So you can prove this as a counterexample. So you can't necessarily do 2k minus 1. And that's because Schmel's algorithm required a certain amount of delay that you're not allowed to have. And again, you could go back to our friend path width that we studied earlier. Earlier, we said it could be done in 3k plus 1 many colors online. But if I give you more information, you can do it in 2k plus 1 many colors, and that's sharp. Okay. And so what I said to Matthew, and again, it was good to have a student who ignores their supervisor. I said to Matthew, I said, well, maybe the reason this is true is because what we're really doing is I'm giving you this thing with a certain path decomposition, and you're building an online path decomposition. So is it true that there is it true that in fact I can online build a path decomposition and then you can just run the algorithm on the path decomposition? The answer is no. And Matthew came up with this really pretty example of a strongly online graph path with 2. It can't be finitely strongly. It can't do that for any finite path width. And it's probably good to finish with a picture or two. And the proof kind of goes like this. You start building those black things are the blue nodes, and you start building the neighbors as paths. And the way to think about what has to happen is the opponent, who you can think about as a partial recursive function, tells you the ordering these things have to be in their bags, as their intervals. He says to say, how are these intervals ordered? Because we don't have to do this. We're building this offline. We know it has path width 2, but we're not going to tell anybody how you build the path decomposition. And when the opponent tells you some ordering, we screw up the ordering by joining these up in some peculiar way, and then he can't rearrange them, so his intersection property goes up. That's the main idea. It was really, really clever. So you connect these things in some peculiar way, and then you do an analysis of what happens to the intervals. So what's a model theoretical framework? Well, speculation. You can have. We speculate that you can have a constant approximation ratio scheme, first order properties, if the Gaefment rank is a technical thing from finite model theory, is below the online neighborhood distance. Current model theory seems to need enriching to fit this framework. Examples, it's kind of a miracle that first order logic, which was designed for classical mathematics, works in other areas. And in some sense, I think it needs to be enriched and refined to seem works. So how to do this? And my belief, I think, will be to put some kind of pseudometric on them. And the other place that you might be able to speculate that things might be doing, you can do further finitization in computability theory. So I think it's a, even though I think you can fool yourself as you're getting older, that you can still cut it. I think it's a really kind of interesting, I think it's a really interesting area. And like John, I guess I get bored with doing the same, even though I never stopped doing things I've done in the past. I like doing new things. I love that feeling of learning new things and discovering things. I mean, I remember when we did parameterized complexity theory, most of that was done in about 3 weeks, the basic theorems. And I just remember at the time just feeling this stuff that, oh, let's do this, oh, let's do this, oh, and I really enjoy doing that. And it's one of those things that I would encourage mathematicians to do. So this paper was in the Bulletin of Symbolic Logic. This one's in the Logical Methods in Computer Science. Matthew asked us, eventually he'll give me the final version of his master's thesis, which is just correcting the typos, which I'll post on my lots of papers on Sasha Melnikov's and Nkang Meng's home pages. And this paper I'm going to have submitted to this proceedings, and there's a smaller paper as well. Well, I'll post that also on my homepage. So thank you and congratulations, John Crossley.